You were standing in a dark backyard at 2 in the morning, phone flashlight off, eyes slowly adjusting to the stars above you. Somewhere up there, closer to Earth than almost anything else in the solar system except our own moon, a tiny rock is quietly circling us. Scientists thought they finally understood what this little rock was, and that answer was strange enough to make headlines everywhere. But new evidence arriving this year says they may have been wrong the whole time. Stick around for this one, because by the end, you will see space rocks completely differently. And if that kind of shift is something you enjoy, sticking with this channel means you get a front row seat to the next one. Its name is Kamo'oalewa, a Hawaiian word that roughly means a fragment dancing in the wind, and it is barely the size of a Ferris wheel. It does not orbit the sun in a simple circle like most asteroids do. Instead, it loops around Earth in a strange, looping dance, always staying close, always coming back, like a dog that refuses to wander far from its owner. For years, this made Kamo'oalewa one of the most talked about small objects in our neighborhood, because almost nothing else behaves this way. Then, in 2021, a team of scientists thought they had cracked its secret, and their answer sounded almost too good to be true. They said this little rock might actually be a piece of our own moon, blasted into space long ago and never fully sent away. That idea traveled around the world in headlines within days. Now, in the middle of 2026, a spacecraft has finally arrived close enough to check, and what it found is not what anyone expected. This is the story of how a rock smaller than a football field became one of the most argued about objects near Earth, and why the argument just changed again. Let us pull back now, before we get into what changed, and start with what most people believe once they hear this story for the first time. Most people who have heard of Kamo'oalewa believe the case is closed, that scientists proved it is a broken-off piece of our own moon, sitting quietly in a strange orbit until someone finally comes to collect it. That belief spread fast, and for good reason, because the evidence really did look convincing. But there is more to this story than a single tidy answer, and it starts long before anyone even knew this rock existed. To understand why Kamo'oalewa caused so much excitement, you first have to understand how strange its home really is. Earth is not alone up here the way most people picture it. We think of our planet with one companion, the Moon, hanging in a fixed and familiar orbit, the same one humans have watched since before written history. But space near Earth is messier and more crowded than that picture suggests, filled with small, drifting rocks that our gravity has quietly pulled into strange, temporary arrangements. Kamo'oalewa is one of a very small group of objects called quasi-satellites. A quasi-satellite is not a true moon because it does not orbit Earth the way our moon does, locked in a clean and stable loop. Instead, it orbits the sun on almost the same path as Earth, and because the two paths are so close together, Earth's gravity gently nudges it back and forth, making it look, from our point of view, like it is circling us. Picture two runners going around a track at almost exactly the same speed, one slightly ahead, then falling behind, then catching up again, forever staying near each other without ever touching hands. That is roughly what Kamo'oalewa is doing with Earth, and it has apparently been doing it for a very long time. This tiny object was first spotted in 2016 by the Pan-STARRS telescope, a wide sky camera perched on top of the dormant volcano Haleakala in Hawaii, built specifically to scan the sky night after night for anything that moves. At first it looked like nothing special, just another faint point of light crossing the frame, one of thousands the telescope catches every year. But when astronomers worked out its orbit, they realized this was not an ordinary passing rock. It was staying near Earth, again and again, on a loop that seemed to have been going on for centuries. The size alone made it easy to overlook. Most asteroids that make headlines are miles across, big enough to end civilizations if their paths ever crossed with ours. Kamo'oalewa is nothing like that. It is somewhere between 40 and 100 meters wide, small enough that if it were sitting in a large sports stadium, you might not immediately notice it from the upper seats. Compare that to the moon hanging over your house tonight, a body roughly 3,500 kilometers across, so massive it quietly controls the tides in every ocean on the planet. Kamo'oalewa is smaller than that comparison can even really capture, more like comparing a single pebble on a beach to the entire beach itself. And yet this pebble-sized rock, drifting almost silently near a planet dominated by something so much larger, still managed to earn its own name, its own research papers, and eventually its own dedicated spacecraft. Something this small, this quiet, this easy to miss, should not have mattered much to anyone outside a small circle of astronomers watching the sky. Think about your own house for a second, and everything that sits quietly around it without you ever noticing. A stray cat that crosses your yard every few nights on the same worn path, never quite leaving, never quite settling down either. That is roughly the relationship Kamo'oleva has with our entire planet, an uninvited visitor that simply never fully wandered off. But its behavior kept drawing attention because the more scientists studied its orbit, the more unusual it looked. Most near-Earth asteroids visit us briefly and then swing away for decades or centuries before we see them again, if we ever do. Kamo'oleva, on the other hand, appeared to have been dancing around Earth in this same strange loop for somewhere between 100 and 500 years already, based on calculations of its orbit. Some models even suggested it could keep doing this for hundreds of years more before gravity finally sends it drifting off into a different path entirely. That kind of long-term stability is rare among small asteroids, and rare things get scientists curious. To put that number in perspective, 500 years ago nobody on Earth had a telescope at all, and Kamo'oleva may have already been quietly looping near our planet the entire time, through every war, every invention, every generation of people who ever looked up without knowing it was there. An object that patient, that consistent, tends to earn a closer look eventually. So teams around the world pointed bigger telescopes at it, trying to squeeze out every bit of information they could from something so small and so dim. One of the most important efforts came from a team led by Ben Sharkey, then a graduate researcher at the University of Arizona, working alongside senior researchers including Vishnu Reddy and orbital dynamics expert Renu Malhotra. They used the Large Binocular Telescope in Arizona, one of the most powerful ground-based instruments on Earth, to capture the faint light bouncing off this tiny rock's surface. That light, split apart and studied carefully, is called a spectrum, and it works almost like a fingerprint for what an object is made of. Different materials reflect different colors of light in different amounts, even colors our eyes cannot see. And by comparing that pattern to samples we already understand, scientists can make an educated guess about composition without ever touching the object itself. When the team compared Kamo'olewa's spectrum to a large library of known space rocks, something jumped out immediately. It did not look like the typical asteroids drifting through that part of the solar system. Instead, its light pattern closely resembled something much closer to home, something humans have actually held in their hands before. Imagine holding two handfuls of gravel from completely different beaches, one from a rocky coastline nearby, and one shipped in from somewhere across the ocean. Most of the time, side by side, the difference is obvious at a glance. Different colors, different textures, different stories written into every grain. But every so often, two handfuls end up looking almost identical, close enough that only a careful lab test can tell them apart. That was the situation astronomers found themselves in with Kamo'olewa. It looked like moon rock. Not a rough match, not a maybe, but a surprisingly close resemblance to lunar material that had been sitting exposed to space for a very long time, weathered and darkened, the way lunar surface rock becomes after countless years of radiation and micro-impacts. The team published their findings in 2021 in the journal Communications, Earth and Environment, proposing an idea that immediately grabbed public attention around the world. What if Kamo'olewa was not a leftover piece of the early solar system at all, but a chunk of our own moon, thrown into space by some ancient violent impact and never fully escaping Earth's gravitational grip? It was a beautiful idea, almost poetic in a way. The moon has been struck by asteroids more times than anyone could count over billions of years, leaving behind craters big enough to see from your backyard telescope. Some of those impacts would have been powerful enough to blast debris clear off the lunar surface and out into space. Most of that debris would have simply drifted away, lost somewhere in the solar system. But this one small fragment, the theory suggested, never quite left home. It stayed close, trapped in a slow orbital dance with the planet its parent world had always circled. Researchers pointed to a very specific place as the likely origin, a young and enormous crater on the far side of the moon called Giordano Bruno, formed by an impact scientists estimate happened somewhere in the last few million years, recent enough in cosmic terms to still look sharp and fresh compared to older, more worn-down craters nearby. The math seemed to work. The colors seemed to match. The timing lined up too, since a rock ejected from a crater that recent, in cosmic terms, would still be young enough that its orbit had not yet had time to fully drift away from Earth's gravitational reach. The story felt complete enough that headlines around the world confidently called Kamo'olewa a piece of the moon, and for years that description stuck. For nearly 5 years afterward, that idea sat almost unchallenged in public understanding, repeated in articles, video essays, and classroom slides. People pictured a literal chunk of the moon quietly circling Earth, waiting patiently for someone brave enough to go and confirm it in person. And as far as most casual observers were concerned, the story of Kamo'olawa was already finished, wrapped up neatly with a satisfying bow. But that picture is about to change, and it changes for a very simple reason. Ground-based telescopes, no matter how powerful, are still looking through Earth's thick, shifting atmosphere from millions of kilometers away, squeezing every last drop of light out of an object barely large enough to notice. To really know what Kamo'olawa is, someone was eventually going to have to go there and look for themselves. That moment finally arrived this year, and what it revealed did not simply confirm the old story. If a moment in this story just cracked something you assumed was true, write it in the comments below, because knowing exactly where people's assumptions break helps decide which mystery we dig into here next. China has been quietly building one of the most ambitious space programs on the planet, and in 2025 that ambition pointed directly at Kamo'olawa. On May 28th of that year, a spacecraft named Tianwen-2 lifted off from the Xichang Satellite Launch Center aboard a Long March 3B rocket, riding a trajectory built to escape Earth entirely on the very first push, something that particular rocket had never done before. Its mission was audacious for a first attempt at this kind of target: fly out to a rock barely larger than a stadium, catch up with it precisely, and physically grab a piece of it to bring home. For the next several months, Tianwen-2 simply flew, quietly crossing deep space while ground controllers checked its health and adjusted its course. Then, in October of 2025, engineers commanded a deep space maneuver, a careful nudge to line the spacecraft up exactly right for the year-long chase still ahead of it. Soon after that, updates from the mission slowed to a trickle on purpose, part of a deliberate strategy to keep public excitement building toward the moment of arrival, rather than spending it early. Months passed in that quiet stretch, the spacecraft drifting further from Earth and deeper into its long, curving path toward its target. By early June of 2026, after traveling roughly 1 billion kilometers, Tianwen-2 finally spotted Kamo'olawa optically for the first time, a faint speck of reflected sunlight against the black. On June 7th, it performed a careful capture maneuver from about 30,000 kilometers away, locking onto the tiny asteroid's position with far more precision than any ground telescope ever could. While the spacecraft chased its target across 1 billion kilometers of empty space, Renu Malhotra and other orbital dynamics researchers back on Earth kept refining their models of exactly how Kamo'olawa's strange looping path had held together for so long, work that mattered just as much as the physical rendezvous itself. Understanding the orbit precisely was not just an academic exercise either. It is the same kind of math that quietly decides whether a wobbling shopping cart in an empty parking lot drifts back toward your car or rolls away entirely, just scaled up to the size of a solar system, patient enough to play out over centuries instead of seconds. In parallel with the spacecraft closing in, something else was happening back on Earth that would matter just as much. Scientists had also pointed the James Webb Space Telescope, the most powerful infrared observatory ever built, toward Kamo'olawa in February of 2026, hoping to gather even sharper data before the spacecraft arrived. What they expected was a confirmation of the 2021 lunar theory, a spectrum that lined up neatly with weathered moon rock, closing the case for good. What they actually found was a spectrum that looked noticeably less like space-weathered lunar material than the earlier ground-based data had suggested. Follow-up observations from the Large Binocular Telescope backed this up, showing a color pattern more consistent with an ordinary kind of asteroid found throughout the solar system, one known to scientists as an E-type asteroid, rather than a genuine chunk of the moon. Imagine spending years convinced a mysterious photograph was a picture of your childhood home, only for a clearer copy to arrive and reveal a house that merely resembles it. That is roughly the whiplash researchers felt watching this new data come in. By mid-June, Tianwen-2 had closed the distance further still, reaching about 2,000 kilometers from the surface, and settled into a careful station-keeping position roughly 20 kilometers away, close enough to finally see real detail on an object that had only ever existed as smudges of light in telescopes before. On July 2nd, it captured the first true close-up image of Kamo'olawa, and on July 6th, the China National Space Administration released it publicly, confirming the spacecraft had officially arrived. That first image showed a small, elongated, tumbling rock, rough and irregular, nothing like the smooth, pale surface of a lunar boulder you might picture in your head. Scientists studying the new imagery, combined with the fresh James Webb data, now estimate Kamo'olawa is roughly 20 meters across on average, smaller even than some earlier ground-based estimates had suggested, and its surface brightness looks different from what a true fragment of the moon should show. It is worth pausing here, honestly, because even the scientists closest to this mission do not fully agree yet on what Kamo'olawa actually is. Some researchers still think a lunar origin cannot be ruled out completely, since a single spectrum, even a very good one, cannot answer every question about an object's deep internal structure. Others now lean firmly toward the simpler explanation, an ordinary near-Earth asteroid that just happens to reflect light in a way that once looked misleadingly familiar. That kind of open disagreement, right in the middle of an active mission, is not a sign of failure. It is a sign that real science, the honest kind, is still happening in real time. There is a strange kind of comfort in watching trained experts admit uncertainty out loud, especially in an age full of confident-sounding answers on every screen. It means nobody rushed to paper over the awkward new data just to keep a tidy headline alive. It means the actual rock in front of them, 20 kilometers below a hovering spacecraft, is being allowed to speak for itself before anyone writes the final sentence of its story. Back on Earth, this uncertainty means something different depending on who you ask. For the small team of scientists who wrote that original 2021 paper, it means years of careful, honest work is now being tested in the best possible way, by direct physical evidence rather than distant guesswork. For everyday viewers watching from their living rooms, it means a story they thought was settled, a piece of the moon quietly orbiting Earth, might actually be something else entirely, a completely separate kind of object that simply looked like home from very far away. Either answer, once confirmed, changes something real about how we understand our own cosmic backyard. If Kamo'olawa truly is lunar debris, it means pieces of the moon are drifting near Earth right now in numbers we never expected, an entire hidden population of tiny satellites born from ancient impacts. If it is not lunar at all, it means Earth's gravity is far better at capturing and holding on to ordinary passing asteroids than anyone previously assumed, quietly gathering small companions from across the solar system and keeping them close for centuries at a time. Either way, the tidy story from 2021 is gone, replaced by something messier, more honest, and in many ways, more interesting. Real answers, the kind that hold up under close inspection, almost always arrive looking a little messier than the neat first draft ever promised, and that messiness is usually the surest sign that the science is actually working the way it should. And here is where this stops being about one small, tumbling rock and starts being about the assumptions we all quietly carry around with us every day. Kamo'olawa spent 5 years wearing a label, Piece of the Moon, that felt so solid and so satisfying that almost nobody thought to question it again once it was printed. That is worth remembering the next time any headline, about space or anything else, hands you a perfectly tidy answer wrapped up in a bow. If this story is the kind of thing that reshapes how you look up at the night sky, send it to the one person in your life who always says space stuff is boring. Because a rock quietly circling Earth for centuries without anyone noticing tends to change that opinion fast. Tianwen 2 is not finished, not even close, and what happens over the coming months matters just as much as what has already happened. Right now, through the rest of 2026 and into early 2027, the spacecraft is settling into a slow, careful survey of Kamo'olawa from an altitude of about 8 kilometers, mapping its surface in detail down to just a few centimeters per pixel, using cameras, radar, and navigation sensors built specifically for this kind of delicate, close-range work. Engineers need this time to choose the safest and most scientifically valuable spot to actually touch the surface, since a wrong choice on a body this small and this loosely held together could easily end the mission early. Because nobody fully knows what Kamo'olawa's surface is really like up close, mission planners built in 3 completely different ways of collecting a sample, just in case. One method involves briefly touching down and firing a gas jet to kick up loose material for quick collection, a bit like tapping a dusty shelf and catching what falls. Another involves hovering and gently vacuuming up surface dust from a safe distance, never fully committing to a landing at all. A third, reserved for the trickiest case, involves anchoring directly onto the surface with small harpoon-like grips if it turns out to be firm enough to hold the spacecraft in place without drifting away. Engineers built this redundancy on purpose, because a rock this small barely has any gravity to speak of. Standing on Kamo'olawa, if such a thing were even possible, would feel closer to floating gently beside a slowly tumbling boulder than standing on solid ground the way we understand it here at home. A firm push in the wrong direction could send a person drifting off into space entirely, never to return, which is part of why every part of this sampling attempt has to be planned with extreme, almost obsessive care. Whichever method engineers ultimately choose, the plan calls for collecting somewhere between 200 grams and 1 kilogram of material, sealed carefully away inside a return capsule built to survive the long trip home. According to the current published mission timeline, Tianwen-2 is expected to depart Kamo'olawa around April 24th of 2027, beginning its long journey back toward Earth. The return capsule itself is scheduled to separate from the main spacecraft on November 29th of 2027, landing at a site near the Jiuquan Satellite Launch Center in northern China, carrying inside it the most direct physical answer humanity has ever had about this strange little object. Once that capsule is safely on the ground, laboratories will finally be able to do something no telescope, however powerful, can ever fully replace: examine actual atoms from Kamo'olawa under a microscope, measure its precise chemical makeup, and compare it directly against real Apollo mission lunar samples, still carefully preserved from the 1960s and 70s. That single comparison, atoms sitting side by side under laboratory light, will likely settle the lunar origin question for good, one way or the other, far more convincingly than any spectrum ever could from millions of kilometers away. There is a quieter, more personal thread running through this entire story too, one easy to miss underneath all the spacecraft and telescopes. The same physics that lets a rock the size of a stadium quietly orbit near Earth for centuries without most people ever noticing is the same physics keeping our own moon locked faithfully in its familiar path above your house tonight. Space near Earth is not empty, and it is not simple, and the next time you glance up at a clear sky, there is a real, non-zero chance a tiny, tumbling, mostly forgotten companion is somewhere up there too, hidden in the glare, going almost completely unnoticed. That is not a comforting thought, or a frightening one, just a genuinely humbling one, the kind that quietly reminds you how much is happening directly above your head that most of us will simply never see with our own eyes. It is easy to walk outside, glance up for a second, and assume the night sky looks exactly the same as it always has, when in reality it is quietly, constantly rearranging itself in ways too small and too slow for any of us to notice without help. Even after Tianwen-2 finishes its work at Kamo'olawa, the mission itself keeps going. After departing in 2027, the spacecraft is planned to use a flyby of Earth to adjust its path, then head onward across the solar system toward a much stranger target, an active object called 311P/Pan-STARRS, a body that behaves partly like an asteroid and partly like a comet, expected to be reached around January of 2035. That means the very same spacecraft carrying answers about Kamo'olawa is also, right now, already on its way to the next unresolved mystery, one still nearly a decade away from being solved. Somewhere out there tonight, Tianwen-2 is still quietly circling 20 kilometers above a tumbling rock most people will never hear the name of, patiently mapping every visible ridge and shadow before it ever risks reaching down to touch the surface. By the time you finish watching this video, its cameras will have captured dozens more images than existed when this sentence was written, each one a small, steady step toward finally settling a question that has genuinely divided scientists for the better part of 5 years. Back here on the ground, none of this requires a telescope of your own or a background in physics to appreciate. It just requires the same thing that got us this far in the first place, a willingness to keep looking up and keep asking whether the tidy answer we were handed is really the whole picture. Kamo'olawa spent years being described with total confidence as settled fact, right up until a spacecraft got close enough to check, and the story quietly cracked open again. That pattern shows up far more often than most people realize, in science and everywhere else, and noticing it is a small, quiet kind of power worth holding on to. Somewhere in a laboratory a few years from now, a researcher is going to lift a sealed container barely bigger than a jewelry box, open it under careful lighting, and look for the first time at actual pieces of a rock most of humanity has never once looked up and noticed. That single moment, quiet, careful, almost anticlimactic to watch from the outside, will likely answer a question that headlines around the world once treated as already closed. Somewhere else, further out past all of that, the same spacecraft that answers this question will already be aimed at its next one, still years from arriving, still carrying the same patient instruments that just spent a year and a half chasing down a rock the size of a stadium. Science rarely closes one door without quietly opening another one just behind it, and Tianwen-2's own flight plan is proof of that. One long relay race between questions that never fully stops. It is worth remembering, on nights when the sky feels perfectly familiar, that familiarity and full understanding are not the same thing at all. The moon overhead tonight is the same moon humans have watched for the entirety of recorded history, and yet scientists are still actively arguing about tiny pieces that may or may not have come from it, sitting almost invisibly nearby the whole time. Somewhere in that same dark sky, whether you can spot it or not, a stadium-sized rock is continuing a loop it may have already been tracing since long before telescopes existed at all. On November 29th of 2027, a small capsule is scheduled to fall out of the sky over northern China, carrying inside it grains of material smaller than sand, gathered from a rock most people will never be able to point to in the night sky. That single moment, a parachute opening quietly over a remote landing zone, will likely close a 5-year scientific argument for good, one way or the other, with real atoms instead of distant guesses. Save this video somewhere you will actually see it again, maybe a playlist called Space Mysteries or something similar, because when that sample finally lands and the real answer comes out, you are going to want the full story fresh in your mind instead of half-remembered from months earlier. Until then, Kamo'olawa keeps doing exactly what it has apparently been doing for centuries, quietly looping near Earth, catching sunlight for a few brief seconds at a time, going almost completely unnoticed by nearly everyone standing beneath it. No headline, no telescope, and no spacecraft has fully finished writing its story yet, and that unfinished feeling is exactly what makes it worth following. Somewhere tonight, whether it turns out to be moon or something else entirely, it is still up there, still circling, still waiting patiently for its own small, quiet answer to finally arrive. And somewhere between now and November of 2027, that answer is quietly falling toward us too, riding home inside a spacecraft that has already traveled 1 billion kilometers just to bring it back.